We're going to talk about Design for Assembly Part 2 and really focus on Boothroyd Dewhurst. So two great references, the product design for manufacture and assembly, which a lot of the examples are taken from, that we're going to talk about today. And then this is a great book specifically for plastic, designing plastic parts for assembly. So definitely encourage you to check them out. Okay, so today's focus is the Boothroyd Dewhurst method. There's several other methods for looking at design for assembly. This today is by far the most popular and widespread, but certainly not the only one out there. And the operating thesis behind this method is that the product cost is directly related to the assembly time, which makes sense. If you can put it together quicker, there's less of a labor rate. The assembly time and the quality, for that matter, are directly related to both the part count and the ease at which the parts go together. And that's where we're going to focus today. What this method involves is systematically looking at the part geometry and how they're fastened and estimating a time to put the different parts together and adding it up and then comparing it with a theoretical minimum part count, namely, in theory, what's the fewest number of possible parts you could have to build the product. And by getting the ratio of those two, you get an overall design efficiency. And this is really, the actual number doesn't matter, but it's really intended as a tool so that as you improve the design, you have some benchmarks or a comparison point. So you know this design is better or worse than that one. And maybe most importantly, it just forces you to take a step back, because usually everything is so rushed to get the actual product working and you're thinking about so many things. This just lets you pop up a level and think specifically about assembly and ask questions. Do I really need two parts? Can I put them together with snap fit rather than screws and things of that nature? So it's really those key insights that are important. And so the two factors that really influence the cost of assembly are the number of parts and then the geometry of how they go together. Specifically, how are they handled, how do you insert them, and then how do they fasten to each other. The way this process works is first you've got to design the product so you have something to work with. Then you'll create an assembly matrix, and we'll work through how to do that, which is going to include handling, so that's the size, the weight, and the orientation of the part. And then the insertion, so how do you align and then secure the parts together? And those are each two separate things. From that, you can calculate the theoretical assembly time, the design efficiency, and then go through an iteration process to improve the design. So starting with the first one, symmetry, which is all about alignment and orientation, there's two angles that we care about. The first one is what we call alpha, which is normal to the axis of insertion. So basically this means how many degrees do you have to end for end the part until you've got it in a similar symmetric position. So if you had a simple rectangle and it goes in this way, my alpha would be 180 because I can achieve the same orientation going in this direction. The beta is the other axis, so the axis of orientation. So how many degrees do I have to swing it through to recreate the same orientation? So in this case, it would be, again, 180. So this would be 180 on alpha, 180 on beta. And the total angle of symmetry is just the sum of both of them. So this would have a 360 degree. And that's one of the inputs to the tables that I passed out. A few additional definitions. So the thickness is the length of the shortest side of a bounding box. And by bounding box, what I mean is if you were to basically create an enclosing geometry that captured all of the geometry of your feature and measure the shortest part of that, that's the thickness. And then the longest part would be the length. So let's just work through some symmetry examples. So here we have a ball going through a hole. What do you think the alpha is? Remembering that's the end for ending. 0, right, because it doesn't matter. It's just going to drop right through. And then how about the beta? 0. Yep, no matter what you do, it's just going to drop in. So that's a really nice design if that's what you needed to do. There's no orientation or alignment. It just drops right through. OK, so how about, well, in this case, 180 for this because you'd have to end for end it. How about on the beta? 0. Yep. OK, here we've got a square that's extruded into a rectangle. So what's the alpha? Yep. And how about the beta? Cool. OK. This one is a square. So what's the alpha?
90.
Yep. And then the beta? Cool. OK. This one's got it's basically a pin or a screw. 360. And then, cool. And then this one has this offset feature on the top.
Technically, it's 180. You just put it in wrong. 360.
Yeah, assuming that that's a good point. Assuming it has to go this way. So this is sort of a well. I guess that's why it's an example. It's a bad design because it's 360 if you want to have it on top, and then this one actually is 360 if you want to have that feature oriented there as well. So you can see the design gets progressively worse, or the greater the angle of symmetry, sort of the more time consuming your design is because it requires more orientation. So based on that, and this is an eye chart right now, but it's on the left side of your handout, you can fill in or enter the table on the left with the combined angle, the alpha plus beta. And then this actually has, I believe, 4 different sections. I've only reproduced 2 here. The top section is for parts that just require one hand, so you can manipulate them with one hand. The second is a hand with a grasping aid, so it might be tweezers or something because it's a small part. So that's a little bit less optimized design. And then going across here, it's broken down into are the parts easy to grasp and manipulate in this column, or are they difficult, maybe small or hot or sharp to handle in this column? Further broken down by the thickness, so are they greater than 2 millimeters thick, which would be easier to handle and a lower score, or are they thin and maybe more difficult to handle? And then the final parameter is just the length of them. If they're longer, they're easier to manipulate. If they're smaller, they're more time consuming. So basically and we'll go through this exercise in a sec, fill in the data going across, get a manual handling code, which will be 2 digits. So suppose it was the first case, the ball dropping through the hole. That's got a combined angle of less than 360, so that would be a 0. And then if it's a relatively large part, it would also be a 0. So that would take a little more than a second to handle. Whereas if you had a part that's more unwieldy, it might take 3 or 4 seconds. Let's see, and then the next set is the manual insertion. So again, this is a multi-part table, but you'll assign a 2-digit code, and we'll work through an example of this. But basically, it's do you have to do anything after the part is installed, and how do you hold it down, and you sort of grade it in a similar fashion. So let's work through this example here. It's basically a multi-part bracket that looks like it's going to hold some sort of a shaft. So we've got a plate, a bracket, a couple of screws, washers, and nuts. And what we'll do is just methodically work through each part. So we'll do the first one together. So the first question is usage or part count, and we're starting with the nut. So there's obviously 2 nuts. What's the, and the dimensions here are in millimeters. What's the alpha on the nut? So for end, 180. Yep. And then what's the beta? 0. Yeah, in this case, assume it's got all the starts it needs, or the orientation doesn't matter.
So usage is 2?
Usage is 2. Usage is part count. So then if we, A plus B is going to give us an angle of 180. And if you look on your chart, what do you get for the handling code? And this would be the chart on the left of what you have. So you'd go in on the left side with the alpha plus beta equals 180. And then the question you have to ask is, are the parts easy to grasp and manipulate or not? I'd say they're big enough, they're pretty easy. So that would be the left side. Is the thickness more than 2 millimeters? So here it's 7. So that's yes. And then it says, is the length greater than 15 millimeters? No. Between 6 and 15, yes. So that's a 1. So this would be a handling code 01, which is how many seconds?
1, 4, 3.
Yep, okay. So basically just follow that methodology all the way through.
I'm curious if they ran this out to hundredths of a second. Is that really meaningful?
Oh, it would if you had enough parts. And it also, it's just a theoretical, so it will let you know what design better or not as good. I think the concern, my guess and seeing is they designed this as opposed to me, so I'm just taking a best guess. But I think if you didn't have that precision, then it would be difficult to grade one design being better or worse than another one. If it was just 1.4, there's not enough significant digits to really figure out which way it's going. And then let me know what you get on the insertion code, which is the table on the right there. And I know it's a little bit hard to read, but the top left said the part and associated tool, including hands, can easily be reached in the location. So I'd say, yeah, that's true. It's easy, so that would be a 0. And then the other one is there's no resistance to insertion. That it's just going to drop right on. So working through together, that would be a 0, 0, which would give us a 1.5. And then the total time is just a matter of the usage times the sum of those two times. So that would say the operation to put on those two nuts is about 5.86 seconds. And then it's just a matter of working through the other ones.
The insertion one? Is there anything that's not 0, 0 for insertion?
Yeah, the last one, the screw.
So screws are because they have resistance.
Right. So the way the Xerox isn't great.
0, 1?
Well, let's see. So the top columns, over here says part added but not secured. So that's up here, and that's not the case.
Right. So it is secured, so it goes somewhere over the
So it's going to go in the second group down,
Oh, all right.
which the key for that is part secured immediately. And then looking there, the first digit number 3 says part and associated tool, included hands, can easily reach the desired location, and the tool can be operated easily. So I would call the first one number 3. And then over, as you slide all the way across, the final option is screw tightening immediately after insertion, easy to align with position, no torsional resistance. So I would call that one a 3/8. And that one gets 6 seconds. So you really get heavily penalized for screws big time because you've got 2 of them. So you're looking at 12 seconds right there, where everything else was sort of in the 1.13 seconds. So that's a big hit. But yeah, everything else by my calculation was 0, 0. How many essential parts are there here?
Essential?
Yeah, so if we, what's the minimum number
I
of,
know that you use it. Well,
let's say everything can be the same material.
there's no rotation. There's no difference in material.
There's only one essential part, right?
Right. Yep, there'd be 2 if they had to be, if the plate and the bracket had to be. But yeah, so that's where it sort of goes a little too far that, you could obviously break it out of 1, but you're going to have a lot of wastage on that extra half ring that you're not using. But that's why it's just such a powerful reference guide to be able to compare two designs and see which one is better. Yeah, so let me see, I'll finish pushing through here. So assuming one essential part and working through the math, I calculated about an 8.8% efficiency on this one. I ended up with roughly 34 seconds to put it together. And then if we look at the redesign, so we've simplified it. Let's say that these are press fit to put the bracket in the pan, and then work through that. Just clicking through it, it's still one essential part, so it's not going to be 100%. But based on that, we see the design efficiency is about 40%. I calculated roughly 7.36 seconds to put it together. So by taking the ratio of 8.8 to 40, I think it's about 4.5 times. So in theory, this is 4.5 times better design according to these metrics. Now, the key thing to remember is everything is weighted differently. So having two nuts in there cost you a lot of time based on this approach. If it actually, maybe they can be put on a little quicker. There's different ways to do it. But it's a good methodology to think about just getting, in this case, rid of the screws. So that's how the method works. Any questions?
Is there a way to use CAD tools to analyze design, have this spit out automatically?
So the Boothroyd Dewhurst folks have built up software that would do what you did on a lookup table automatically on the software, that you could just pull it down. I don't know, and it's a great question whether they've got integrations with CAD or not. It seems plausible. It seems like a solvable problem that they could, and that'd be pretty cool if you could, instantly, like in your bill of materials, say your design efficiency is whatever. Yeah, their website is just www.dfma.com, Design for Manufacture and Assembly. Yeah, so I'll have to go check. Yeah, it's a great URL.
So it seems like there is some kind of judgment that has to be applied to this.
Yes.
So is that all described further in the book?
Yes, part of that is in the book, and also part of it's just the basis of engineering experience and practice. But yeah, there's definitely a large amount of judgment that needs to be applied. Like in general, we'll typically use we'll try not to optimize out the screws, because I know I can rework it, and it's a very simple, low-cost thing that our factories can do. Whereas for this design, what it would tell me is I should take it all out of one piece of progressively stamped metal, but I'm going to have more wastage. There's a classic example that they do about, it's basically a bracket that has a cross in it, and the minimal theoretical parts would say you should do that all out of one piece, but you can show that due to the scrap, it's actually cheaper to build it out of two and put it together. So that's where the judgment comes in. But this is just, if we think of looking at any design through multiple lenses, this is just one lens to look at it through for DFA. Another one would be to look at it for part cost. So if this was made out of gold, then I'd care a lot about my scrap, whereas if it's made out of cheap like scrap iron, I probably don't care. So just balancing all those things.
But this still gets you roughly there anyway, because it gives you, say it's a minute to put it together, it's a minute at $4 an hour or whatever.
Right.
You know how much the material costs. So it's not like it ignores it, it's simply you add it to the...
Exactly. And it would also depend, suppose I'm building this in Beverly Hills, to think of one of the more expensive places I know. My labor rate's going to be insanely expensive, that I would care the most about that and probably the least about scrap. Whereas in the other thing, if I'm building it in a very low-cost labor base, but it's out of gold, then I care so much more about material and not at all about labor. But this gives us a way to sort of think about those trade-offs. And we find often people think, either they focus on the engineering, they get the thing working. Hopefully they think about quality in life and how long that should last. They think about design for manufacturing parts, but typically people won't think as much as a specific discipline about design for assembly, which is a very different thing. And this, if nothing else, is a sort of a forcing function to take a step back and be like, all right, well, let's look at this stuff and try to make it better. And again, it's definitely not the intent that you should optimize the design perfectly before you go into production. Like, it's important to match cost, quality, and schedule. Once you're building in the millions of units, then absolutely you want to optimize every penny out of the design. But an easier design will have much better quality and lower cost. And the decisions you make up front cast a long shadow, because as you're talking about, if you go and tool a design that's not as well thought out as it could be, it's going to cost you more later. So with anything, it's like finding those right balances of a multivariable system all coming together with a time axis. So.
Scott, I know in Germany there's a big push for design for disassembly and recycling.
Yes.
Are you getting any pressure in the United States for recycling?
We haven't hit the point where we're getting pressure. We're starting to see people, including myself, really interested in that. So it's, I don't look at it as the frosting on the cake because I'm a strong environmentalist at all. But it's, we haven't seen people walk in the door and say, you need to do this. It's more like, oh, it would be nice, we've got this thing working, can we add in this ability to break it down into the core components so you can recycle the plastic, throw out the boards. There's a, and I'm blanking on the name, but there's a strong push at one of the centers out of MIT for design for sustainability, where they really look at that. Because as you've probably seen, there's just terrible things happening in China with the circuit boards, where they're in villages being melted down and incredibly unsafe for the people and the environment, and anything we can do to not have that happen. I mean, if you think of the amount of e-waste that's recycled, it's mind-numbing. So getting better designs that don't force that to happen is really important.
From the U.S. government?
I haven't seen it yet. I mean, the ones we see are, a while ago, RoHS, or ROS, Reduction of Hazardous Substances, ROHS, came in, meaning you can't use heavy metals. You can't use, the biggest offender was solder. You can't use leaded solder. And certainly every factory we work with in China is all RoHS or ROS certified, like they won't touch lead. Because often in Europe you can't use it, in the US you could, but then you have to have two different products and it's a pain in the butt to keep track of them, so you make everything lead free. In Europe there's REACH and WE, which is reduction of, well, it's a greater reduction of substances known to be environmentally dangerous. So we see that happening. We have Prop 65 in the US, which is really local to California, but if you want to sell, and it's a labeling restriction that if you have one of the substances known to the state of California to cause cancer, you have to put a sticker on it. But it's better if you cannot use that, because then A, it's the right thing to do, and B, you don't need to label it. But yeah, I think that's sort of the next wave that I'm looking forward to, when that is a requirement. I'd like nothing better than people to jump up and down. And I know the factories, many of the factories we deal with are in China, and they're incredibly responsive to consumer demand. They're very, very clean these days over there. There's very little waste, but they realize to service the customer, they've got to be responsive. So it would be great to see that happen more.
Does that stuff push into waste reduction during manufacture as well? So like the die cutting industry, for example, is like massive waste.
Yes. Yeah, we would see for stamped metal or things like that, all of the scraps would be recycled because it's money, and China is very, very efficient. There's no, as you walk around the factory floor, there's never any waste baskets, just because if there's waste, there's a problem. So it's a good indication, like not to have waste baskets forces the issue. But we see those as incredibly efficient. Great, well, thank you for coming. Really, really appreciate it. This is awesome.